All right, welcome to AOML HRD Science Seminar. This is Shirley Merlot. We have a visitor here. If you have questions, please type them in the chat as well as unmute when it's time. And I will be unmuting folks just so that as a courtesy for our speaker. Xiaomin Zhang, I'm sorry, I'm thinking of Xiaomin. Zujin Zhang will be introducing our speaker. Zujin?
Okay. Good morning, everyone. Welcome to our AOML seminar. Yuqing and I, we met a long time ago through our connection with Chinese project. And Yuqing, right now, he is a professor in University of Hawaii. He graduated from China with bachelor degree and master degree. Then he went to Monash, right? Yeah, Monash University, pursue his PhD degree with Greg Holland. You know, most of the hurricane people probably know Greg Holland. And after he graduates from Monash University, then you stay there for a while.
For 5 years.
Yeah, for 5 years. Then he moved to, he gets a professor job in University of Hawaii. And he is, contribute to all TC research part, all aspect. And today he's going to talk about his recent theoretical work, but he did a lot of NWP work also. He has published 230 papers, and he won the top 1,000. What is that title? Top 1,000 Earth Science, most cited Earth Science scientist. I think very few in our field. The tropical cyclone field. I think Frank was on the list, and he is one of that. With that, I think give the floor to Yuqing. Yuqing, go ahead.
Thank you for Shijing for the introduction, and also that's the really very my great pleasure to have a chance to visit the HRD. And the people here say, "Oh, we have never been in HRDs before, and you're a hurricane fan." Yeah, that's true, because I had attended the hurricane conference in 2010. I planned to visit here, but the people here are always in the conference, say nobody here. So that's I say next time come here, sorry for it. So anyway, I have a good opportunity to attend the 85th annual meeting. Last 3 days, I enjoyed the meeting very much, because I'm seeing a few people come from the academic side, because this is the main operational side and the observation space. But I think we need more interaction. That's the reason I came here, because I think for academic researchers and we can have we should consider the operational needs, and also observational side can motivate some of the ideas for us to pursue some scientific issues. So I think that's very important for the interaction between the academic and the operational part. So today I bring one new topic, because I say new because for Robert just mentioned, say, vertical structure, I worked a lot. But yes, I have published some papers, and we try to understand how the structure of the storm to affect the intensification of the storm, the TC. But today I focused on some baseline research. Why I say the baseline? Because we don't know if there are any conditions favorable, how fast the storm may intensify. Let's come back to about 10 years ago. Frank Marks asked a question in the tropical list, storm list. Say we have the MPI theory. Whether we can have the MPIR theory. MPIR, that means the maximum potential intensification rate. So we have MPI, maximum potential intensity. Whether we have the MPIR. So that's motivated me to think about. So that's about 10 years. I spent about 10 years to work on this theory. So I think this is very close now, and we are here now. So that's the reason I say That's probably a memory of your email and communications in the community. So that's really stimulate me to work on this topic. So today I will briefly introduce the time-dependent series. As we know, for tropical cyclone intensification, we always say positive feedback, this effect. But the problem is it's always qualitative. No one have quantitative measure of the intensification rate. So this is the major contribution, I think, to the current understanding on this problem. So my seminar will start from a review of the classic views on tropical cyclone intensification very briefly, because this community is everyone knows about the best classic views. Okay. So then I will introduce the early efforts toward time-dependent series. So we have the first one, I can say that's the Kerry Manners in 2012, but there are some deficiencies I will mention later, followed by the existing problems. So that's mean current series, there are problems. It's not perfect. So then we try to solve some problem, not the whole problem, part of the problem. So and also analyze the causes. What causes the problem? Okay. And only once we know what caused the problem, we can solve it. We can try to solve the problem. And then the new development that's mainly from my group. So we spent about it. We think about 10 years ago, but we in the last 5 years we have extensive studies, okay, to pursue the way to solve the problem, existing problem. And finally, I will introduce some thinking and the applications. So the theory, perfect. That's the perfect hurricanes. And any applications, and what's the issue we should go forward. Okay, that's we need to we will discuss, and that's also a reason why I came here. Okay, so because the theory is perfect, but the hurricane is never perfect, and then we try to work which imperfect part can contribute to reduce the high MPIR. Okay, so that's the major logical of my talk. Okay, so I think everyone knows the hurricane. We have for the theory classical views on intensification. There are statistical theory. That's the hypothesis. We don't see the same theory. Theory is the closed ones. So with the closed and basic dynamics, that's the core theory. But those we only can consider the hypothesis. Basically, it's just describe the positive feedback in the boundary layer convergence, which converges friction equipment pumping, and then support the convection in the IOR region, and then pressure drops, and then cause the tropical cyclone to intensify. So convective scale and the storm scale intensify together. And then the wish mechanism, that's the proposed by Kerry Manners, mainly the tropical storm intensify, wind increase, surface flux increase. Okay, energy comes from the ocean, eventually the storm, right? So this is another positive effect. And another hypothesis, this is also I call it the safety theory, balance dynamics. Balance dynamics says that we use the direct dynamic background, but the theory couldn't define the dynamic heating. You have to give the dynamic heating, and then you can diagnose the secondary circulation, and then you know how the different structure of the storm can affect the intensification rate of the storm. But repeating, there are no clues still. Okay, that's for the semi idea of the series. Or the series, I can say, or the positive descriptions, just to emphasize one of the certain positive feedback, not a closed series. Okay, here I just already mentioned CISC and WISH. There are differences. CISC is the global interactions, the storm scale and the convection in the IOR region. And WISH is different. That's the focused on the area under the IOR. Okay, so like under the IOR, the wind increase, surface flux increase. Okay, so this is the wind increase, the potential energy. You can say that that's the energy from the ocean increase. The storm may intensify more. That's the positive feedback. Actually. So for the balance of the vortex dynamics, that's the question. You can see this is the tangential wind equation. Okay, we just consider this the symmetrical storm for simplicity. Okay, so the interaction potential, you can see that's the first two term. That's the positive because the inflow and the hurricane is the positive absolute velocity. That's the if you have inflow, you always have the tangential wind increase. Okay. And the vertical elevation, that's the normally the secondary for the scale storm. Okay, so that's just to support the convection. So this term probably the secondary. Of course, that's in the inner core above the boundary layer. Of course, it's also important because the maximum wind is always in the boundary layer, trend toward upward. But the last term is the frictional effect. Is always negative. Okay, so if we consider the tropical cyclone intensification, there are two components: one is the intensification potential, one is the frictional weakening potential. So this will simplify the problem. Okay? So the frictional effect is proportional to the CD because the drag coefficient. And for the balance dynamics, that's a given eye overheating, and then you have the strong inflow. Inflow, you have the absolute positive absolute velocity, and that's the positive large tendency. This tendency increase the intensity, the V increase, and the inertial stability increase. Inertial stability increase, that means the absolute velocity increase. This is a positive effect as well. Yes.
Sorry, stop. So what you're saying is we are starting with a warm core already in the system here.
It's an anomaly.
Yes, that's an anomaly. Yes, that's an anomaly. Yeah. We can consider that's an ideal, very ideal. That's axisymmetric. Okay. We consider this axisymmetric. You assume there is storm there.
Remember, this is a balance, so there is no.
This is a balance.
Change is kind of zero.
Yeah, that's a balance. That's a balance point. Okay. So that's the anomaly. Yes, that's the. Okay, so I can summarize here all classic views of positive distribution of certain positive feedback processes like the situation and the balance dynamics. But there are some new efforts. I consider new efforts is to try to quantify tropical cyclone intensification rate by developing physically or dynamically based time-dependent series. Okay. So I will introduce those early efforts. So why we try this way? I think there are two points I need to mention. There are potential applications to tropical cyclone intensity forecasting. Because if we have a theory, we really can know if we have a hurricane, and then we can estimate how fast the storm will intensify. Once we know the track roughly. Okay. The second is the theoretical basis can be used for understanding climate change impact on tropical cyclone intensification. Because there are climate science very care about the MPI previously, but in recent years they try to understand whether tropical cyclone also intensify more rapidly under the global warming. So there are no scientific basis, no theoretical basis. They just consider the storm becomes stronger and must be intensified. But the theory may provide this basis. That's for basic understanding. Okay, so early efforts. There are two early efforts. One is based on the energetic point of view to develop a time-dependent theory. The second is dynamically based time-dependent theory. So I will introduce these two theories very briefly. So we know the energetically based, that's the Carnot heat engine. So this figure just shows you the classical views of for tropical cyclone, assume a tropical cyclone like a Carnot heat engine. What's going on? Tropical cyclone hurricane get the energy from the ocean and dissipate the energy to the ocean as well. Okay. To the end, so then the whole system, hurricane system, get the potential energy. That's why I used the PE here. And of course the SE, that's the enthalpy flux from the ocean. And then for the heat engine, we have the thermodynamic efficiency. Okay, so this is what the system can get. Okay, and then there are dissipation here, dissipative heating, dissipation, frictional dissipation. So once the two terms balanced, PE equals the frictional dissipation, and that's the MPI. It's so simple. That's the MPI theory we carried in 1986. That's a lot of mathematical formulas. And then if we understand this from the energetic point of view, it's very simple. Because under the steady state must be balanced, right? The energy input and energy dissipation must be balanced. So we can use this diagram, phase diagram, I think that's my famous diagram, but I don't know how many of you pay attention or use this diagram. And you can see the energy input or power generation is a function of the wind speed, linear function of the wind speed. So that's the horizontal axis, that's the intensity of the storm. You can see VA, Vmax. And then and also you can see the power dissipation is a function of the cubic of wind speed, maximum wind speed. If we apply this under the IO or near the inner core region, that's a good approximation. Okay. So eventually, what's the MPI? MPI is here. Okay, because that's the intercept, and you can get the MPI formula. That's the very famous one. You can find in many publications. Okay, but from my diagram the phase diagram is so simple. What's going on before the storm reaches the MPI? That's where we have the net energy gain to the system. Okay, because this is the increase much faster with the wind speed. And the energy input is linear. So at the beginning, the linear function, of course, is larger than the cubic ones. So this is positive area. This is energy gain. So that means the energy can provide to the system to intensify. Like we drive a car. At the beginning, we give the gas, then car accelerated. And then eventually, if you keep the gas at the same level, and the car will reach a steady state. Okay, so that's the parking is like this. That's why you can consider this way. So if we accept this concept, then differences. So potential energy minus the energy frictional dissipation, that's the total energy change to the system. And what's going on? This is if this is greater than 0, of course, that's the intensification. That's conceptually I proposed in 10 years ago. Okay? And then we try to work out. Okay, so this is the work is done by the Azawa and Shikokuwa, okay? The Japanese. Okay, so we can see the energy input power generation. This is the thermodynamic efficiency and the energy dissipation. Okay, dissipation rate. So this is energy gain, total energy gain, as I mentioned, total energy gain. Okay, so this is where you have add this because this is the when the storm is quite weak at the initial stage, you're weak, and not the all potential energy can convert to kinetic energy because there are some gravity waves, propagated wave, and propagated wave. So there are efficiency. So how much energy can be used to intensify the storm? That's the introduced the mu here by these orders. Okay, but you can see if you assume this is the kinetic energy change in the inner core region. This kinetic energy change, energy gain becomes kinetic energy. Kinetic energy. Eventually, you get the formula like this. Okay? This is the final equation. The intensity change. That's the intensity rate. It's the function of the MPI and the function of the intensity of the storm is served. The second term, of course, is caused by the friction. That's caused by the friction. But the first term is the potential intensification caused by what? By the energy gain from the ocean. Okay. But unfortunately, in their work, they propose that the mu is a constant, 70% around. But that's the problem, because if you work on the steady state for this formula, what's going on? What do you get? If you get the steady state, this is becomes 0, right? If this side becomes 0, this means the Vmax only 70% of the maximum potential intensity, because this is the theoretical MPI. Okay. We consider this is the theoretical MPI, because this is if we use this is that is the theoretical MPI. So this is there are some deficiencies first. The second is you can see the maximum intensification rate for the maximum occur where? When the Vmax is 0. The second term is always negative. That's the frictional dissipation. So that means the storm at the incipient state intensify more rapidly. It will never happen naturally. Okay. But observation shows the hurricane intensify rapid intensity always occur in the intermediate intensity, like a 30 to 40 meters per second. Never have a rapid intensity when the storm have 5 meters per second or 10 meters per second. So that means the theory there are some deficiencies. Okay. So this is the energetically based theory. theory. The second theory is the Carey-Manoa time dependent theory. That's dynamically based. What's the dynamically based? It uses the equation in the slab upon layer. Slab upon layer. You can see the momentum equation. I don't introduce this in detail. I just give you the ideas of how he worked out the theory. So this is the momentum equation and the entropy budget equation in the boundary layer. Okay. Integrate this equation in the boundary layer. In the assume a slab boundary layer, and then you can get this equation. This equation is just the budget equation for the entropy. The last equation. And with this equation, with some assumptions, I introduce some assumptions here. So he assumed the tropical cyclone is assumed to be axisymmetric and in summer wind balance above the boundary. And then the radius maximum wind is the material surface. Material surface, that's very restriction assumptions. If you have this assumption, and then the V max and the R max can be nearly a constant. That's the material surface. Absolute velocity or relative velocity nearly conserved. The third assumption is the absolute angular momentum surface and the saturation entropy surface are nearly conformed. Doesn't mean parallel. Okay. So angular momentum is the I wall and the and also the entropy surface is parallel. Following the current. This only occurs in the only satisfied in the mature state. In the early state, they're almost perpendicular because isentropic surface are horizontal, and the momentum surface is in vertical. Okay, so this assumption is really called the no buoyancy. Yeah, no buoyancy in that case. So that's the so eventually, you got with these assumptions, Carey-Manoa got the theoretical PMR, okay, intensification rate. That's also two terms, very similar to the energetically based equations. It's exactly the same, okay. So the first term is the intensification potential. The second term is similar to dissipation because the negative sign here. The problem is, you can see the dissipation or the weakening rate is determined by the CK, not CD. That's unrealistic. Okay, again, unrealistic. So compared with the previous energetically based theory, this is another problem. Other problem is the same, like the maximum intensification rate occurred at the incipient state of the tropical storm, tropical cyclones. Okay, this is the why in when Carey evaluated his theory, he used the not from the zero, and not from the time equals zero, but if after some time, say only the storm reaches the immediate intensity, the theory can apply. But the early state, the theory failed. Okay. So this is the problem. Okay, so the problem I mentioned already, I just summarized here. The first energetically based theory, there are steady state intensity is only 70% of the corresponding MPI. So this is the unrealistic. So the second is the maximum intensification rate. You can see this is the intensification rate, okay, occurred at the V max equals 0. That's the incipient state of the storm. You can get the maximum intensification rate here. And with the storm intensified, the intensification rate becomes smaller and smaller. Eventually, it stopped intensifying. That's the steady state. Observation. That's the observation we copied the paper here. So the dots is the overall intensification rate from the overall storm, many storm. Horizontal axis is the intensity of the storm. So what do you see here? The maximum intensification rate, that's the dots, occur in the intermediate intensity. That means the 60 to 80 knots. That means 30 to 40 meters per second. That means the theory couldn't capture the observations. Okay. So we try to identify what's the problem. Okay, the problem is I just mentioned already. So this is I have a question mark here. So that means the theory there's some problem there because the dissipation supposedly is proportional to the drag coefficient rather than the extended coefficient. Okay. And the second is the assumption of the material surface. We also found from numerical simulations that's not a good approximation. Okay. This is not conserved. So we that's the relative angular momentum is not conserved following the radius maximum v. We should remove this assumption as well. And then the another assumption is the Morse neutral thing. That's not satisfied in the intensification stage, but only in the mature stage. So we try to avoid these problems. This is what I started the project. Okay? The first, I try to separate the energetically based and the dynamically based. Okay? And we can solve the problem by introducing just one change, small change. You can see in the previous question in the original paper, they have this is mu, right? Mu is 70%. But what I did, I tried to introduce a dynamical efficiency. Dynamical efficiency instead of thermodynamical efficiency there. That's thermodynamical efficiency, that's the heat engine. But dynamical efficiency, that means how much potential energy you can use to spin up the tangential wing. We know this is from dynamical hydrology, we already know. Ross radius deformation determines how much energy partitioned to the rotating component or the gravity component. Okay. So this is the very we can consider this is the dynamical efficiency is a function of the inertial stability. Since the inertial stability is inversely proportional to the Ross radius deformation. So this is what I did. This is in the first paper, we succeeded. We met the observations, modified one parameter. So I show you the results. That's the numerical simulations. So you can see this is we have the different SST. Okay, in the Western Pacific and also in the North Atlantic due to the same thing. Okay, we use the profile. Okay, the tropical mean profiles and under the different ST, and we run the model for many times on sample T. Okay, so eventually we get the intersection rate as a function of time here. Okay, as a function of time. The red one is the simulation, and the green one is the theoretical one. Theoretical. That means I have a formula, right? We use the inertial stability as a dynamical efficiency.
So what was the efficiency that you?
Efficiency is a function of the inertial stability in the core inertial stability.
Okay.
Inertial stability. Okay, shown here. This is what we did. This is what we did. Okay. So what do you see here? It's very interesting. So for all cases, we can follow the theory, can capture the observations, the numerical simulation quite well. That's a full physics model, not a simple model. And then we, if you plot the intersection rate, it's a function of intensity. This is the horizontal axis is the intensity. So it's matched quite well. The maximum intersection rate occurred at the intermediate intensity rather than the very weak intensity. That's because we use the introduce the dynamical efficiency. This is sort of one problem.
Is this numerical simulation based on ideal case or?
Ideal case, but I will show you later. I have a dynamically based theory conversion also. Okay, so this we just change one parameter. So then we try to solve the problem that's in Yuqing theory, because in his theory he used assumed the relative angular momentum to conserve. That means the radius maximum weight in the material surface. I have to remove this assumption, so I use the momentum equation. I have to use the momentum equation and also entropy budget equation. Okay. And the major assumption we use is this balance. The key assumption is the additive effect, additive tendency is balanced by the surface flux. Okay, this makes sense because the advantage is already called advantage, and the surface flux is trying to compensate. That's the balance. That's the only assumption I use. Okay, with this assumption and this momentum equation, we can get the equation like this. Okay, and also we can use this assumption. This is just the bottom layer, the angular momentum change following this entropy service. That's the bottom layer is equal the change at the top of the bottom layer, nothing else. But it makes sense because that's the second one that we're assuming already. That's what makes sense. Okay. Consistent for the assumptions. Okay, you may ask the balanced assumption whether the good or not. We shown from numerical simulations. That's all simulation. Okay, we have the North Atlantic, West North Pacific, different water profile, different SST. You can get the time tendency nearly zero, and the duration term and the surface flux nearly balanced. That means the balance assumption is much better than what Curry did. So the relative angular momentum is conserved. That's the material surface of the RMWS.
Yeah, earlier you showed an equation which is dynamics. And what is this first equation on theta e?
This equation, first equation, second equation is equivalent.
Oh, okay, thank you.
Entropy and the theta e is equivalent. They are changing consistent. So this is supporting material. Say we use the assumption can support it. Is supported by the regular full physics model simulation. Okay, then let's see. We need to work on this one. Okay, there's one term here. I just mentioned here. We need to estimate this term. This term is easy to get if you assume that the neutral I were same. Because thermal wind balance, you can integrate following the angular momentum surface. Integrate from the top of the boundary layer to the outer flow layer. The boundary layer is stored. So what they did originally in Curry-Manoa theory, that's the equation they got. Let's assume what they assume. For this term, this is just a thermal wind balance. From this equation, you can integrate following the angular momentum surface. You can get this equation. I just introduced one parameter again here. This parameter is A prime. We introduced the A prime because this assumes the parallel of the angular momentum surface and the entropy surface. We say not perfect. Yeah, perfect. There may be perpendicular as A prime. Okay, you introduce the way A prime. A prime can be zero. When the storm, no storm. Okay, and then may come to 1 because one is the mature state. Okay, so this is the only parameter we introduced, and with this parameter, eventually we get this equation. This one, the new IR equation I said. Okay, so the only difference is just the difference is the A. If you compare it with the energetic based theory, the A, if we change the A, becomes the E. That's the same. So that's why I combine the two theories, and we get the converge, and then we can use the only one framework to verify the theory. Okay, with this, and we need to work out what's the A. How we determine the A? We know the A change from 0 to 1. Okay. And the next consideration is a function of the relative intensity. The relative intensity, let's say, is defined by the Vmax divided by V MPI. Because once the storm intensifies to the MPI, it becomes 1. Of course, I add a power here. That's the A. We introduce the A pi A here. Okay? But A equals greater than 0. We need to define how to define it. We use calibration, use a numerical model, use observations. Okay. Okay. So what do we got? We got the N equals the 1.5. Okay. 1.5. That's what we get. But eventually you get the equation like this. There are no any curvature storm size parameters.
Did it have a distribution or it was an average? What is it?
I will show you. Very interesting here. Okay. Very.
Yeah, I can imagine.
Yeah, you can imagine. Okay, so that makes sense from the theoretical thinking. That makes sense because if the Vmax is NPM is 0, that's 0.
Yes. What's the issue? Was the boundary higher?
Boundary layer high. It's the
boundary high makes in the I wall.
That's the under the I wall. Yeah, it's about 2 kilometers we use. That's mixed dynamic and thermodynamic boundary layer, not the just one. Okay, because we use the budget equation for the entropy and also for momentum.
Take up the inflow layer.
Yes. That's also estimate. We also tried the different edge, and then we found 2 kilometers. That's the best fit.
Yuqing?
Yes.
So A, as I understand it, A is essentially just the degree to which the angular momentum and the entropy surfaces are parallel.
Yes,
So
correct.
if they're completely perpendicular, it's a 0 or
Yes.
it's a 1 maybe.
Zero, from 0 to 1.
But the intensification rate is greatest when they are the furthest apart
Yes,
from being parallel.
yes,
Okay.
yes.
So you're mentioning best track data and idealized simulations. So you're doing this calibration, and obviously there's no observations of entropy.
Okay, I show you.
That's the simulations you use that for, right?
Simulations. We have the equation like this. Okay. We have the equation like this, and then we know the MPI. We can calculate the MPI. We have the current intensity. We have the intensity change tendency from the simulation from our best track, and we just A is just calibrate. A is unknown, only one known parameter.
That's from the simulations.
Yeah, and we use the unknown as a function plot plots, okay,
Yeah.
as a function of relative intensity. I'll show you the plots. Okay. See what do you have? Okay, so this is from observation. So we have several lines. One is n equals 1, n equals 1.2, 1.3. Because the theory doesn't include any negative effect from any environment.
Right.
So we need to be able.
Yeah.
What's the envelope? Envelope for the 1.5 is the best one. That's the fit. Of course, there are some points outside of the curve. But only there's
Well, the atmosphere's in it.
function also has areas.
The environment.
Yeah.
It's not,
Yeah. And from numerical simulation, you see, that's the very good fit. 1.5. Okay. We have the 1.2, and
Yeah, so Rob, think about
1.5.
Rob, think about it this way, that there could be a million ways that you could have that incongruence.
Mm-hmm.
Baroclinity, different structures, shear, whatever,
Mm-hmm.
and cause that incongruence. So you should have a spread. And
Yes.
1.5 is kind of the best fit.
Best fit to the envelope. Because it's the maximum.
I was surprised it's so tight. Surprised it's so tight.
Yeah.
So, as I understand it, then I think what you're saying is the intensification rate is a function entirely, or maybe not entirely, of the incongruence between those surfaces, right?
Not entirely.
But okay, because
But also there's other.
okay, so then the next question is, and Frank mentioned this a few minutes ago, that incongruence is a statement on buoyancy. right?
Yes.
So the more buoyant it is, the greater the intensification rate.
What were you getting?
Okay, so
Yes.
because I know Kerry, I feel like he's talked about,
Yeah.
oh, you don't need buoyancy.
No.
So you.
No, dynamic control. Dynamic control.
Okay, all right.
Yeah, the buoyancy is kind of implied.
Yeah. And also,
Works.
ours were mentioned about the A. Okay, what affects the A? I will mention that.
Yeah. I'm trying to understand, sir. I mean, the problem, excellent work. The problem that I'm seeing here is, if you take the momentum equation that we're talking about, in general, the momentum equation, three-dimension, includes the heating in terms of pressure gradient forces. That's
Yes.
what is related.
Yes.
Here I don't see a source term at all.
You couldn't see because the heating from the surface. Okay, that's the potential energy from the surface determines the heating. Because we have the iron, assumed the iron already. We assume the storm there already.
So which term will determine? A is the
We
one.
don't, this is the first term.
The way I would think about it is, his potential energy surfaces are dictated by all these heat.
Oh, okay.
Yeah.
So he's assuming that they have shape,
Yeah.
which implies that there is some heating going on.
Yeah.
That is being driven by the pressure gradient forces. So that's the big assumption.
Yeah.
I mean.
And like the MPI
if you
theory.
look at the model, that's what's going on. He's reduced it to the static stability shape.
Angular moment.
Yeah.
Okay, these are angular moments. Surface.
Yeah. Okay, so how good compared with the numerical simulation? So that's why I have to show you one example from North Atlantic. We have the northwest Pacific, the same. Top is the west North Pacific, SFT, and sunny. And then the lower panel showing you the result with the SFT sorted by the sunny sorted by the ST. Okay, we got the solid line is the numerical simulation, and the test line is the theoretical intensification. Intensity change, okay, not intensity rate here. Let's just compare the intensity. We can time integration, this equation, and compare with the numerical simulation. Perfect. Okay. So you couldn't, it's really hard to believe sometimes, okay? At the beginning, I said, oh, so I can catch over over 95%. Right? So that's a good solution. Okay. How about the observation? This is verified in the theory with using the best practice. So the upper boundary is theoretical estimation. The lower boundary is observations. So because we have 6 hours data, and then we can estimate the intensification rate, okay, in color, in shading, okay, in shading. And the vertical coordinate is the MPI. Horizontal axis is the intensity of the storm, current intensity. You can see the current intensity and the MPI. So the maximum intensification rate is occurring in the medium intensity, okay? That's what we saw, right? 30 to 40 meters per second. So you can get the maximum intensification rate. So of course, this is only the top 99%. Because the theory considers the ideal conditions. We compare the theory, can compare with the perfect condition in observation, but observation are not perfect ones. So we now use the 99% top, 99%. So you can see the maximum is here, theoretically is here. Okay. And then we use the relative intensity. The horizontal axis becomes change from the intensity to the relative intensity, and the vertical coordinate is still MPI. What do you see here? The maximum intensity occurred at around 60% of the relative intensity. Okay. This is the theory. What's the observation? Very similar dependence on the relative intensity. So that means the relative intensity is very important for the intensity forecasting. Okay. So then we also did some sensitivity experiments. For example, that's an analytical solution. Because the equation, we can get the solution. Okay. And then you can see we use the different XT here. So different MPI. Different MPI. What do you see here? That's the intensification rate. Faster, slower, right? What determines this? That's the MPI determines. MPI squared. From this equation, you can see the MPI is a function of relative intensity, but also the square of the MPI. So this can explain why for the super intense hurricane, then more rapid intensification as well. That's the theoretical basis. For global warming, say, if the global warming, we get the same more rapid intensification.
So the ordinance Vmax or VMP?
Where?
The ordinance, your y-axis.
Y-axis is the intensity.
It's IR or is it Vmax?
Vmax. That's given the MPI. Given the MPI.
Okay.
That's in different colors here. Given the MPI, and then you can see how fast and how long the storm reaches the MPI, reaches the maximum intensity. You can see once the global warming, for example, and the ST increase, the MPI increase as well, and the storm reaches the maximum, the steady state faster.
So go back one figure. I wanted to get the units on IR.
Units, that's the every 6 hours. Every 6 hours.
Okay, so 6 hours.
6 hours. Oh, this is the
meter per
this is 6 hours. 6 hours.
So meters per second, 6 hours per 6 hours.
Yeah.
So if we wanted to get a 24-hour limit, multiply by 4.
Mark R4. Yeah.
Extrapolate.
That's exactly. You can see the theory and the observation.
Right. So I was trying to get an idea of whether, what John Kaplan and Mark Ingrid defined as the 5 percentile on the odds.
Yeah.
Was like 30 meters per second or so in 24 hours.
And later we can provide from observation. We can find what it is. You can estimate. Use this figure. You can estimate it from the observations. For the forecast, I can say when the storm, where the intensification rate.
Well, the thing I like about it, Yuqing, is if we have an estimate of what it could be.
Yes.
And we know what it is. We know that we're not, in a balanced state or in a state that would meet these criteria.
Yeah.
I mean, obviously, environmental conditions could.
Well, that's the issue.
Yeah.
That's another issue. I will address.
Baseline, like you said.
Okay, because of time, so I will address that as well. Okay, that's what I'm working on. Yeah, obligation. Yeah. So okay, so this are some implications first. You can see large area during the rise state. Because if you look at the vertical column here, so the difference is quite small. It's relatively small, but during the rapid intensification stage, you can see the large areas. That means yes.
So that means it's A and B. That means What is it?
Oh, the first we just try to see the different MPI.
Right.
And to see the intensification rate and how far the storm to reach the MPI.
Right.
In a lower panel, we just say the initial condition. So the storm is a weaker storm and a strong storm. And what the theory can predict can
So
how the
for
theory can.
example, orange curve on a B, it will take about 48 hours
Yes, yes.
to reach its I.
To reach the
Predicted RI.
particular RI, yes.
Yeah,
Yeah. So you can see when the storm is quite weak, 2 weeks. Like 1 meter per second, the storm takes a week, and then can get the slowly get the intensification. But if the storm get the intensity 10 meters per second, that's the very quickly can get the intensification rate. So that means the storm generally can take a longer time. Then the storm become a proper storm, then intensify very rapidly often. So that's the worst thing, because in the nature we have a lot of depressions, but not all depressions can intensify. Of course, just remember, environmental condition is one aspect, but dynamically, the theory tells you also. So even environment is very, but the storm at a very weak stage couldn't intensify.
So you just used a phrase that was really interesting. You said once the storm becomes a proper storm, then it can intensify. So I think a lot of our research is focusing on how do you get that storm to that proper storm,
Yes,
right? That's that
yes.
organizational stage, for
That-
at which point then RA.
Okay, that's what I say. I will say there are some issues. That's why I come here.
Yeah.
So because I have considered we have to have a perfect one, and then see what causes the imperfect.
Yeah, so Ron,
If you have no perfect ones, you don't know where it is.
Right, well, that's.
So,
reality.
I mean, a basic issue is that these theories are based on an axisymmetric wave number zero structure.
Yes.
And how you get that wave number zero structure to that point where it would do this is what you would get.
Yeah.
Oftentimes, like you were showing in the Ian case.
Yeah.
We get a lot of asymmetry. So think of it as wave number 1, 2, 3, and 4.
Misaligned, dry air intrusion.
Yeah, I have idea. I will give you
Wave
explanation
numbers
for it.
are affecting that advection because it's not axisymmetric. It's got a lot of in and outs going on, or waves around it.
Yeah, I experiments and they will discuss later. But there are some new developments. So that's the here in the paper. That's the impress, the JS impress. So we include the diabatic heating and the diabatic heating. That's the really makes sense in diabatic heating because the storm is stronger, very strong storm. Diabatic heating may be important.
Yeah, so this is an interesting thing because
I show you here. So this is the we use it without the diabatic heating. We have two curves here. So this is the relative intensity. So this is the no diabatic heating intensification rate. What for the 6 hour intensification rate? This is with the diabatic heating. With the diabatic heating, you can see the intensification rate become larger, but in order to shift toward the more intense side.
So please define what you mean by dissipated heating.
Okay.
There's a lot of talk about dissipated heating, the boundary layer and stuff like that, but I want to know what you call
Okay. This is the boundary layer.
Okay.
The boundary layer. And then there are important aspect in the theory is we consider the feedback. Dissipated heating will reduce the surface heat loss.
it. Right, and
But in the previous or series, they had never considered this negative. So I have the delta and gamma is heating, but the delta is there are how much go to the ocean.
So it reduces the heat flux because you're warming the atmosphere, so the air sea contrast is reduced.
Reduce, yes, with that. Okay.
yeah, and so the big question is, do we ever observe that? I don't know that we have the data to really know yet.
Yeah.
I don't think we can characterize dissipated heating from our obs yet. Certainly not from drop zones.
I feel like June is done.
I already had many discussions with June.
I know.
So he reviewed my paper, so.
I know Joan is the reviewer, and that's why I'm bringing it up.
Oh, okay.
Because Joan and I have looked at it a lot.
Okay. So you can see there are some observations. This is the irregular estimate, the black ones. Okay. So you can see the theory underestimated intensification rate a lot on this side. With dissipative heating, you see perfect. You can capture all the observations. The black one capture the red one.
Yeah. and I still go back to, we need to be able to characterize what that is.
Okay. That's if you look at the paper carefully, more carefully.
No, I'm thinking about
Oh,
observation.
yeah. Also, I will discuss with the journalist.
We need to look at the fluxes in
Yeah.
the boundary layer. I think
Let's see what it is.
the altius is going to be.
And I think I will skip some of the new development because there's some very mathematical ones, and that's a secondary to the major theory.
So one of the things to think about, Yuqing, is
Yeah.
working with Hyun Suk and with the sail drone, and the waves and the spray and all these different things that they talk about that generate this speed of heat.
Yeah.
We talk about evaporation of the spray that's generated by. And so the heating part really is the part that I'm not quite clear about. And, to me, it's a jargon term, just maybe.
Mhm.
And people talk about it, bandy it around, but I don't know that we actually have characterized what that means.
Yeah.
And how it actually happens. I mean, your description of it and, sounds like what I've heard before, but I don't know that we've seen it. I used to have arguments with your colleague out in Hawaii, who,
Yeah.
we wrote a paper together with him and Morrison, talking about Steve Businger. And, he talked about, dissipative heating. He wrote a whole section in that paper talking about dissipative heating. And when I read it, I couldn't quite understand what he was talking about. So.
Okay, we can discuss more on that. But this is the Borg consideration. Okay, very.
Until you throw dissipative heating in, because I don't understand it.
Yeah. Okay. So I have some other. Tell me.
Yeah, so my question is like, dissipative heating is trying to warm up the bottom level temperature, but meanwhile that can cause the air is less saturated, so that can increase the moisture difference between the
Yes.
So-
That's the.
And also I believe some studies show that
That's the effect is secondary. Okay. In my theory now, I discussed with Kerry Manor and Richard Rotuno. We discussed a lot. Okay. So these framework they both accepted and reviewed. It's all papers. Okay. They accepted the concept now.
We'll let you conclude it. And then we can talk.
Yeah. Okay. So I very quickly here, and that's I included the effect of isosolar impaction, so I will skip. This is not important here. And also, there are another aspect is the air temperature differences in the environment is so important. That one is the implicitly included the enthalpy flux in previous studies. But in my work, we have a air temperature differences is 1 degree, 2 degree, or 3 degree. We can do the explicitly to estimate how important. We found that's very important. Visibility is important, but just 1 degree air temperature differences can cause equally important, almost the same increase to the MPI and the intensification rate. So this is a new, I think that's a new understanding currently. Okay. So I will not go to the detail, go to the paper and say just impress. Okay. So I just summarize this part and then the application very briefly. 1 minute. Okay, so the new simple time dependent theory of problem in confronted, which overcome several weaknesses in previous work. And several new developments have been achieved. There are the inclusion of distributed heating and the isosolar impaction and the discrete air temperature differences, as I mentioned. So these are just the effects of the scale. But the very important one is the maximum intensification rate is proportional to the square of the MPI. Okay. So this can be used to explain the global warming impact on hurricane intensification rate. Okay, very briefly. Okay, so what's any application of this? Okay, the first, we know we can get the maximum intensification rate at some stage. The relative intensity around this 60%. We can estimate from observation for operational use. Because once we have a hurricane and we know the track somewhere and a 5-day forecast track, we can follow the track and calculate the MPI, and then we can estimate the maximum possible intensification rate. This is what currently not exists. Marketing area have the RI index. Right? RI index is low dynamic basis. So this is physically dynamically based estimate. The second is the environmental effect. how can you introduce the environmental effect? Okay, previously we have the dynamic efficiency E or parameter A here. Okay, so we have the parameter A or E here, but now A and E root up in this function. So what else we need? We need to introduce one parameter B. That's the environmental effect. So this effect can explain by the effect the environment can affect the dynamic efficiency. And if the vertical wind shear, not all the potential energy can use it to convert dynamic energy. So we should reduce the dynamic efficiency. The second is A prime. A prime is like the ventilation. Maximum the momentum service and the entropy service. If they have dry air intrusion, destroy the perimeter. Okay, so this will reduce the efficiency as well. So B can be less than 1, rather than 0. It's between 0 and 1. How we can get it? We have observations, best track data. We have numerical simulations. We can have different environmental conditions, vertical wind shear or whatever we can add, and then we can calibrate the B based on observations. That's the paper we are working on now. We got a very perfect results because we have first we identify vertical wind shear is the first factor, most important, and then we have the middle level reflectivity. We have the upper level divergence also can be important factors. So this is the environmental factor we can get. We use the machine learning to estimate the B. Okay. And once we know the B, we can use it to this equation to time integration. That's just a second. You can get the intended forecast. And the third one I mentioned already. That's we use the best track data to estimate the trends of the identification rate from observations and also from the climate change simulation. So this is another issue. Okay, so why I'm here? As the Rob already mentioned. In our theory, there are no any 5 parameters. Why? Because this is a perfect storm. We assume that the storm is favorable, the structure is favorable for identification. So this is the numerical results some time ago. The different rates of maximum wind here. You can see different rates of maximum wind and a different shape. Rate. You can see we have the different rates of maximum wind, different shape, outer shape. This is the compact vortex, broad vortex. That's the Rob knows quite well that they use the red to retrieve the wind field. They find the different identification rate. That's the lower values. You can see the smaller storm intensify more rapidly, and the broader scale storm works slowly, and the larger storm intensify slowly as well. So that means that's the numerical results. Observations show the same thing, but the problem is how can you incorporate this into the theory? That's another story I'm thinking now, and also the reason why I came here. So I can 3 blocks here. Under favorable environmental conditions, the evolution of the TC is largely driven by its initial state, including the intensity and also the structure. And the TC-RI is sensitive to initial TC structure, but current theories only deals with the optimal structure. Okay. We don't have the structural parameters.
What's the optimal structure in this? Is that blue line, for example, the blue curve? Is that what you consider the optimal structure?
I probably agree.
That's the like the blue ones. Yeah, not the blue ones.
Okay. And so I would say Ian was probably close to the red line.
Close to the red line.
Because it was a broad vortex.
Broad.
Yeah, slowly decaying, relatively speaking.
Yeah.
Right.
And that's decaying. The structure also affected the decaying.
Yeah. Right.
Yeah.
Right, okay.
So the last point I said that's very important. I think the HRD can collaborate. So TC response to external effects may strongly depend on TC structure, because the perfect storm very quickly depend on the structure. Must be the large storm you have vertical wind shear, the small storm you have vertical wind shear. Their response to two are different. So that's the direction we should go further. Okay, I think that's the topic. It's also I'm thinking. Okay, that's my time over now. thank you for your attention.
Yes, thank you. Thank you, everyone. Do you have some questions online, and I'd like to get to those. So thank you for sticking around. And where's the chat box? Oh, here it is. Okay, the first question is from Luke Graber, Professor Wang. In addition to the role of friction heating, this work is based, as was Professor Manuel's, on MPI on static SST. SST change is related to intensity as well as ocean conditions and storm ocean, of course, which can be controlled in idealized simulations. How would your results change if you substitute something like dynamic potential intensity in place of MPI?
Okay, that's the, I think that's the very good question. And indeed, we haven't included any air-sea interaction current series. Because that's still first step. That's the next step. We will consider how the air-sea interaction can affect the MPI.
We'll call that C.
Yeah, once we have the MPI, it can't, because the air-sea interaction always normally is a negative effect. Reduce the MPI. Reduce the MPI, of course, reduce the integration rate. That's the thing we are considering, yes.
And one final question here on the chat. Did you compare your theoretical MPIR to real extreme cases like Hurricane Patricia?
That's exactly one of my PhD students currently work on this case. Patricia. So this is without dynamic heating, we underestimate the MPI. With dynamic heating, we really can get the maximum intensity of storm. And then the integration rate, actually the theory can capture the integration rate. Right? That's surprising. That's why the PhD just have a proposal.
Yeah, I'd like you to chat with Xiaomin about your boundary layer optimization in your model that you're using the needs of this paper.
Yeah.
To see if you really need it or there's something else.
All right, thank you again. Thank you for those online. We will conclude this seminar and thank you again.